Hi, welcome to Problem Solving Expert. In this video, I would like to talk about hypothesis testing for means. When we want to compare one mean against one value, when we want to compare two means, small samples, when we are going to compare two means, but when we are having dependent samples, they are not independent, or the independent was the previous one, but dependent samples. And of course, when we also want to compare means, but you are having large samples. This time I won't be talking about other type of hypothesis testing. In all the cases it will be about normal distributions. So actually I'll be talking about t-test and z-test. I won't be talking about ANOVA, analysis of variance, which there will be another video for ANOVA when you are going to compare more than two means. And also I won't be talking when you have non-normal distributions. So I won't be talking about non-parametric test. But before starting to talk about hypothesis testing, I would like to talk about where we are in terms of the problem-solving process and where we want to go in terms of this problem-solving process too. So at this point, we have defined what is the problem, and we have defined a metric, a technical primary metric, which will be our output or our response. That is our success indicator. And also we have evaluated our baseline performance, we have evaluated defined our objectives, and we have validated the measurement system. We have done gauge R&R studies or uncertainty studies to validate the measurement system. Now the next step is to brainstorm several potential sources of variation, all the potential X's or potential factors that are creating variability. It is very important to take in consideration that the question that we should ask is not what is creating the defect, what is creating the problem, but the question is what is creating the variability, why we are having this spread, why we are having this standard deviation. And basically the question, as I have said, is why we are having this big value, why we are having this small value, why this is high, why this is low. So what is creating variation? Of course, we have defined which are our specification limits, we have defined our PPNs. The objective is to identify what is creating this variability and reduce the sources of variation, so at the end we will be having a smaller variability in the process, and of course our performance will be much better and the probability to have defects outside the specification limit will be smaller. So that's why we have to brainstorm all potential sources of variation. Of these potential sources of variation, we have to classify them in four categories, which are constant. The constant one, they are not changing, so they are not creating variability. Maybe they can affect to the mean, they can create a bias on the mean, but they are not creating variability because they are constant, they are the same, and we are going to discard that one from our analysis. Also, we have to identify which are the standard operating conditions. Which are standard conditions? Things that we know that they may affect our response, may create variability in our response, but we already know what should be the standard condition. For instance, maintenance. So we have to make sure that we are having the correct maintenance to the machine. We are not going to run later a design of experiment with good maintenance and with bad maintenance, with good raw materials, with bad raw materials. We are not going to do that. We already know that those things do affect the response, and we have to make sure that those are under the standard conditions. So those also should be discarded. Of course, before we have to make sure that they are at the standard condition. So the other two are the ones that we are going to analyze, which are controllable, things that we can control. Not necessarily we are right now controlling those ones, but we could control them, and noise or non-controllable factors. So, of all these potential sources of variation, the ones that we are interested to analyze are the controllable and the non-controllable or noise. Now, of those, we want to classify them in two categories: highly likely and lowly likely factors, highly likely and lowly likely factors. The lowly likely will be taken and we are going to put those in standby. So right now we are not going to do a further analysis to those ones, but we are going to take the highly likely ones and we are doing maybe a design of experiment, for instance, to identify which of those highly likely are significant and which of those highly likely are not significant factors. And later, of the significant factors, we want to classify them on vital factors, which are the 1, 2, 3 variables that are creating 80% of the variation, 90% of the variation, and the trivial many. All the other factors that are not creating much variability, they do affect, they are significant, but the effect is small. Of course, we want to focus on the vital ones. So at the end, this is the process that we are going to follow. This is a screening process, the screening process. We brainstorm potential factors, we discard the constant and the standard operating conditions. Also, we want to classify in lowly likely and highly likely. Lowly likely are outside of the analysis. Highly likely will be taken to further investigation. And of those one will be classified in non-significant and significant factors. Of the significant, we will identify which are trivial, which are vital. But of the vital, then we are going to focus on the controllable ones. We already know that this factor is creating variation, but we cannot do anything on that one. And maybe it can be the moisture or the environmental conditions, and if we cannot control those conditions, or well, the experience of the operator or whatever. So those are things that we cannot control. So we are going to focus on the vital factors, vital and controllable factors. Of the vital and controllable factors, we are going to first do what we call steepest, which is an optimization process, and we are going to find a feasible region. And of the feasible region, we want to identify a robust operating condition. And the robust operating conditions is which are the operating conditions of the vital controllable factors that minimize the effect of the non-controllable factors. We want to make our response insensitive to the non-controllable factors, and those will be the robust operating conditions. At this point, we are not there yet. At this point, we have just talked about the output, about the response, our baseline, validated the measurement system, and we have brainstormed all potential sources of variation. So right now, let me say that I want to identify which of these potential factors are highly likely and which of those potential factors are lowly likely. And one of the tools that we can use to identify which are highly likely and which are lowly likely are hypothesis testing. Hypothesis testing can be used in several phases in the problem-solving process. For instance, when you are selecting a project, you can use hypothesis testing. When you are defining the scope of the investigation, you can use hypothesis testing. When you are validating the measurement system, you can use hypothesis testing. At the end of the project, if you want to identify if there was a significant change, baseline and performance after improvement, you can use hypothesis testing. So hypothesis testing can be used in many phases during the problem-solving process. But in this time, I would like to use hypothesis testing to identify which are the highly likely and which are the lowly factors. So right now, we have potential, controllable, and noise factors. So we have brainstormed potential sources of variation, controllable, non-controllable. And of those, we have to ask, do we have historical data for those potential factors? If the answer is no, I don't have historical data, well, then use your experience, maybe voting, maybe the voice of an expert, maybe a nominal group technique, etc., to identify of these potential controllable and non-controllable factors which can be lowly likely or could be lowly likely and which could be highly likely factors. The highly likely will be taken to further investigation, perhaps a design of experiment. The lowly likely, they will be in standby. Maybe we are going to need them later or not. But if you have historical data Then, how to define which are highly likely and lowly likely? You can take advantage of your historical data, and you can do a statistical analysis using the statistical data. My recommendation at this point is to analyze one factor at a time, Of course, I'm ignoring the potential interactions, and that's something that I have to talk about later in the process, but at this time, analyze one factor at a time. And doing this statistical analysis, if, according to the statistical analysis, there is a significant difference on the response, depending on the levels of the factor, well, you will define that that's a highly likely factor. If there's not a significant difference, you will define that that is a lowly likely factor. Statistical analysis. What statistical analysis should we do? Well, it depends. So you have to classify your potential factors into quantitative factors, continuous, variable, or discrete or attribute factor, good, bad, it has, it hasn't, experienced, not experienced, education low, medium, high, etc. So you can have different levels. So that is discrete. And also your response, your output, your Y, you have to identify if that is a quantitative, continuous variable, or if that is discrete, attribute, pass or fail, good or bad. And then, depending on that classification, of that combination of what type of data you are having for your response and what type of data you are having for each factor, you will decide what the statistical analysis should be done. For instance, if you are having a quantitative output and you are having a quantitative input, then you can use a correlation or a regression. If you are having a quantitative output and you are having a discrete or attribute input, you can use hypothesis testing. If your output is discrete but your input is quantitative, then you can use a discriminant analysis or you can use logistics regression. There will be another video which I will be talking about binary logistic regression, ordinal logistic regression, etc. And of course, if both are discrete, then you can use a contingency analysis, which is or chi-square. Chi-square also is one sort of hypothesis testing when both are discrete or attribute. In this video, I'm going to be focused on hypothesis testing. For hypothesis testing, your response is quantitative and your input, your factor, your potential source of variation is discrete. And then, well, we are going to use hypothesis testing. Let me start talking about hypothesis testing, and I would like to compare two means, small samples, normal distribution. So I will have to talk about independent samples, by the way, and I will have to talk about t-student test. Let's do that. Before starting to talk about the procedure of hypothesis testing, I would like to talk about the selection of hypothesis testing, to select or to decide what hypothesis test to use. There are many sorts of hypothesis testings. Hypothesis test for means, hypothesis testing for variances, hypothesis testing for proportions, etc. But even for means, there are several options. So let me talk about that. Let's assume that we are having this situation. We are having historical data. We are having our output, our response, our technical primary metric, which is the particle size. And we are having different sizes of particles. And also from historical data, we have two Millers, Miller A and Miller B, We are having three operators, John, Mary, Louis, and we are having different speeds for the Miller. And well, we are wondering which of those factors are highly likely and which of those factors are lowly likely. As I have recommended, taking advantage of the historical data, we can do statistical analysis analyzing one factor at a time. For instance, in the first example, if I want to analyze the particle size, which is our output, our response, and the Miller, which is our input, what type of statistical analysis should we do? Since our particle size is a quantitative variable, so the y, the output, is quantitative, and Miller is A and B, that is discrete, then we should do a hypothesis test to analyze Miller against the particle size. We want to know if the Miller is affecting to the particle size or not, according to the historical data. By the other hand, we also are having three operators, John, Mary, and Louis. What statistical analysis should we do? Since our output, our response, which is the particle size, is a quantitative variable, and John, Mary, Louis are also discrete, they are not quantitative, we also should do a hypothesis testing. And finally, speed, that is a quantitative, and particle size is quantitative. Since both are quantitative, to identify if there is a potential relationship between speed and particle size, we should do a regression or a correlation. In this case, I'm not selecting logistics regression or chi-square because our output, our response, our y, is not discrete, it's continuous, which is the particle size. If, for instance, our response was a big particle, small particle, then our output would be discrete. If it's inside the specs or outside the specs, good shape, bad shape, or good, medium, low size, for instance, in those cases will be discrete, and then we should use logistics regression with the speed and chi-square with operator and Miller. But this is not the case. In this case, we are having a continuous metric, quantitative metric, then we should use regression for speed and hypothesis testing for Miller and operator. Now the next question is hypothesis testing. What hypothesis testing? There are several types of hypothesis testing. As you can see here, hypothesis testing for means. If you are having normal distribution and if you are having non-normal distributions. For non-normal distributions, actually, those are not hypothesis tests for mean, but those are hypothesis tests for median. And there are different types of hypothesis tests for median, which we call non-parametric test. In this video, I'm not going to talk about the different type of non-parametric tests that you can use. But I will be focused on normal distributions. And for normal distribution, if you want to compare one mean, if it's a small sample, you will be using one sample t. If you have a large sample, then you will be using the z-test. If you want to compare two means and the samples are independent, then you will be using t-student test for two samples. But if they are dependent samples, you will be using 2-pair t. Later, I will be talking about that, about what is dependent, what is independent. And if you want to compare more than two means, then you should use ANOVA. If we go back to our example, the Miller, for instance, we are having Miller A and Miller B. So I want to compare if the mean of particle size for Miller A is the same or is different than the particle size for Miller B. Then I want to compare two means, the mean of particle size for Miller A and the mean of particle size for Miller B. If they are different, if there is a significant difference between those two, then my conclusion will be Miller is a highly likely factor. That's a factor that very likely is affecting to particle size. If after the hypothesis testing, my conclusion is there is not a significant difference in particle size between Miller A and Miller B, in terms of the mean for particle size between those two, then that is a lowly likely factor. So then that means that I want to compare two means. Means of particle size for Miller A, mean of particle size for Miller B. For that case, if you want to compare two means and they are independent samples, later I'll be talking about that, then I have to use two sample t. So that is the first test that I should do for to compare two means. Now, by the other hand, in the example of particle size and operator, we are having three operators. We are having John, Mary, and Louis. So I want to compare if the mean of the particle size for John is the same than the mean for particle size of Mary, and is the same of the mean for particle size of Louis. If my conclusion is the means are different each other, there is a significant difference, the conclusion will be that's a highly likely factor according to the historical data. If my conclusion is there is not a significant difference among those three means, that means that that is a lowly likely factor. So in this case, I want to compare three means: mean of particle size of John, mean of particle size of Mary, mean of particle size of Louis. That means that since I want to compare more than two means, for operator I should use ANOVA, analysis of variance, to compare the three means. In this video, I won't be talking about ANOVA. There will be another video later about ANOVA. So in this video, I'm going to be focused on this four type of hypothesis test. And well, using this example, I would like to start with the two sample t. So that means that I want to sort the data in this way. Let me just very quickly do this. And I will be using this data. So I will say Miller A and Miller B. So this is the Miller. And for Miller A and Miller B, I want to use the particle size. So I have particle size, which is the output, for Miller A and B. For instance, for Miller A, we are having the first 6 of them. The particle size is 15, the particle size is 11, the particle size is 17, particle size is 12, particle size 16, and particle size 14. For Miller B, particle size of 8, particle size of 10, particle size of 13, particle size of 9, particle size of 11, and particle size of 7. So I want to compare if this mean is significantly different than mean for Miller B. And that's why I have to use two sample t or t student test to compare those two means. Well, let's start that, and I will be talking about the procedure for hypothesis testing. Hypothesis testing, when we want to compare two means, independent samples, normal distribution. Well, in order to introduce this test, first I would like to mention that usually when we are having a population of size n, which is having a mean and a standard deviation, keep in mind that we are using Greek letters when we are talking about populations, and we are using Latin letters when we are using samples, data of samples. Well, usually when we are having a population, since it's not possible in most of the cases to have the entire data of the whole population, usually we are taking a sample. From that sample, size n, we are having a mean and a standard deviation for that sample. The mean and the standard deviation of the sample won't be exactly the same than the mean and the standard deviation of the population. If this is a representative sample, it will be close. It will be close each other. It will be near the mean from the population than of the sample, of the standard deviation, but it won't be exactly the same. So if we do the same thing and we take another sample, which is having size n, can be the same size or different sizes, which is having a mean and a standard deviation, it will be the same thing. The mean and the standard deviation of the second sample won't be the same than the mean and the standard deviation of the population. And the mean and the standard deviation of the second sample won't be exactly the same than the mean and the standard deviation of the first sample. But still, both are coming from the same population. So in theory, there shouldn't be a significant difference from a statistical point of view between those two samples, because both of them are coming from the same population. The thing here is that currently we are having two samples. We are having sample which size n size n for Miller A, which is having a mean of particle size for Miller A and the standard deviation for particle size of Miller A. And here we are having the sample size, the mean, and the standard deviation for Miller A. And by the other hand, we are having also another sample, size B, with a mean for Miller B and then standard deviation for Miller B. And here we are having the data for the second sample. But the question is, are these samples coming from different populations, or maybe they are coming from the same population? In other words, the difference between those two, is that a significant difference from a statistical point of view? Of course, if we take a look to the data of the sample, we will see that the mean is 14.17 and the mean is 9.67. So most of the cases people state, of course, the particle size for Miller B is smaller than particle size for Miller A. But I wouldn't say that immediately. You shouldn't jump to conclusions immediately from the data that you are having from the samples. Because again, as I have said, the samples always, all the time, they are going to be different, always. Even if both are coming from the same population, the mean and the standard deviation for each of the samples will be different each other. And there will be as many means and as many standard deviations as number of samples we are having from the same population. But that doesn't mean that they are coming from different populations, or that doesn't mean that the difference that exists between those two, three, among those 3, 4, 5, are significant from a statistical point of view in terms of the differences. The differences shouldn't be that different from a statistical point of view if all of them are coming from the same population. But at this point, we are having two samples, and we don't know if the difference between those two is significant from a statistical point of view. In other words, if they are coming from a different population or not. As I have said, yes, 14 is bigger than 9. But I don't know, perhaps if I take another sample from Miller A and another sample for Miller B, it can happen that for second sample, 9 will be the value here and 14 will be the value here. Because as I have said, you will be having as many different means and standard deviations as number of samples you are having from the population, from the same population. So, of course, if there is a significant difference between those two, even if I take another sample, they will be bigger, and this will be smaller. If I take a third sample, this will be bigger, this will be smaller, if there is a significant difference from a statistical point of view. But I don't know that yet. In order to conclude if they are coming from different populations or not, or maybe we don't have enough statistical evidence to conclude that they are coming from different populations, well, we have to do a hypothesis test. So, we are having two samples. They are independent each other. I will assume right now that they are coming from normal distribution, there is a normal distribution for this data, and there is a normal distribution for this data. You know, if your sample size is small, you can use Kolmogorov-Smirnov test. I invite you to take a look to my video here in YouTube about normality test. And well, when your sample size is small, you can use the non-parametric test, which is Kolmogorov-Smirnov, to check that. But well, at this point, I will assume that they both are normally distributed, and they are independent of each other. So well, what should I do in order to evaluate, in order to test if the difference between those two means is significant from a statistical point of view? Well, let's do hypothesis testing. For hypothesis testing, here we are having the procedure. Step number 1, define the practical hypothesis. For the practical hypothesis, you have to write what you think is happening. For instance, I think that the particle size for Miller A is bigger than the particle size for Miller B. And the reason of that is because particle size is 14.17 and particle size is 9.67. Then what I think, which is my hypothesis, my practical hypothesis, is that particle size for Miller A is bigger than particle size for Miller B. And that's what I will be writing here in the practical hypothesis. And I will say that a practical hypothesis is particle size is bigger for Miller A. Okay. Step number 2, define the null hypothesis. Null hypothesis, we are converting the practical problem into a statistical problem in terms of parameters. There can be different parameters that we can test. We can test means, we can test variances or standard deviations, or we can test proportions. For the null hypothesis, the parameters always must be equal, or the difference between those two should be always 0. So some of the options that we may have are, for instance, that the null hypothesis is that the mean for Miller A is equal than the mean for Miller B. Or also we can have that the null hypothesis, the standard deviation or the variance for Miller A, let's use standard deviation, is the same than the standard deviation for Miller B. Or for instance, and this is not the case because we are not talking about proportions or percentages, but this is used for attributes, the proportion of events for Miller A is equal than the proportion of events for Miller B. In this case, I don't want to check. Right now I'm not evaluating if the standard deviations are different or not. But I'm quite interested to check if the average, if the mean of particle size for Miller A is bigger than particle size for Miller B. Then the parameter that I will use to check, to test, will be the parameter related to the mean. And that's the one that I will be using here. So let's do that. The null hypothesis, as I have said, always will be equal. The null hypothesis is that the mean of particle size for Miller A is equal to the mean of particle size for Miller B. Take a look, I'm using Greek letters. So that means that the hypothesis is not for the sample. The hypothesis is for the population. Then my conclusions will be about the population. I'm doing inferential statistics. I'm taking samples, I'm analyzing the data of samples, and I will be making inferences about the population. And that's what I'm doing. I will be doing inferences about the population. Now, define alternate hypothesis. Also, we can have different options for alternate hypothesis. For instance, if I have selected the mean, one of the options for alternate hypothesis is, for instance, the mean for Miller A is different than the mean for Miller B. Also, another option, it can be that the mean for Miller A is bigger than the mean of particle size formula B. Or also it can be that the mean formula of particle size for Miller A is smaller than the mean for particle size of Miller B. It depends on what is my practical hypothesis. For this example, since I think that the mean of particle size for Miller A is bigger than the mean for particle size for Miller B, I should use the second option. But just to start, and to be safe, I will be using they are not the same, they are different. And then that is the one that I will be selecting. I will be selecting this one as my alternate hypothesis just to be safe. Then the alternate hypothesis will be that the mean of particle size for Miller A is different than the mean for particle size for Miller B. Now, establish risk that can afford. Establish risk that can afford. Usually, in most of the books related to statistics, you will read that you can use a 95% confidence level, which means a risk of 5%, or you can afford an error of 5%. But actually, you should not generalize. You have to think what you are testing. What is the risk of concluding that the null hypothesis is right or the alternate hypothesis is wrong? So depending on that, then you will decide what is the risk to take. And then I will explain about that. So basically, I will state this. There are several options. One option is that the reality and your conclusion. There are several options. The reality is that the null hypothesis is right, which means that mean for Miller A is equal to mean for Miller B. The reality, it can be that the mean for Miller A is different than the mean for Miller B. The conclusion also, it can be that mean for Miller A is equal than mean for Miller B, or your conclusion, it can be that mean for Miller A is different than mean for Miller B. If the reality is that they are not different and you conclude that they are not different, you are right. You have done a right decision. If the reality is that the particle sizes are different and they depend of the Miller, and your conclusion is that they are different, then not a problem. You have concluded right. But the problem can be that if the reality is that the particle size are the same, but you conclude that they are different. So basically, here you are rejecting the null hypothesis, because by the way, if you reject the null hypothesis, then you will accept the alternate hypothesis. This is what we are testing. We are testing the null hypothesis. So at the end, the conclusion will be about that. We reject. If we reject null hypothesis, we accept alternate hypothesis, or we fail to reject the null hypothesis. So it can be that the reality is that they are not different, but you conclude that they are different, then you are having an error. That is an error. And also it can be that your conclusion is that they are the same, but that the reality is that they are different, then that's an error as well. This error, they are called in different ways. So, for instance, one of them is error type 1 and error type 2. Also, this is known as error alpha and error beta. Error of suppliers, the suppliers and the customer, for instance. So there are different ways that they can be called. So here, the question, we have to define alpha. Alpha is the risk that we can afford. How much is the alpha that we can afford? And there are several options. It depends or there can be many options. It depends on what are the implications of making an error, making a mistake. So here the question is, what will be the effect, or what will be the consequences if we conclude that Miller is different when in reality the particle size is not different depending on the Miller? Is that a big thing, or is that a big issue, or is that not a big issue? What is worst? Is it worse to conclude that Miller is affecting to the particle size? Because, by the way, if I'm stating that the particle size is different depending on the Miller, that means that the Miller is affecting to the particle size. What is worse? To conclude that Miller is affecting to particle size when in reality it is not, or is it worse to conclude that Miller is not affecting to particle size when in reality it is affecting? Well, for this case, by the way, alpha can take many numbers or several numbers. Let me just to state some options. For instance, for alpha, 10% of alpha is a big error. 5% of alpha is a medium error. 1% of alpha is a small error. Can I afford a big risk? Should I afford a medium risk, or should I afford a small risk? In this case, I would prefer to take a big risk. Why is that? And that means that I would like to take a risk of alpha equal to 10%. Risk of 10% or 90% confidence level. Why is that? Well, let's see what will it happen. Right now, in the problem solving process, I am identifying which are the highly likely factors and which are the lowly likely factors using historical information, historical data. If I'm using historical data, I'm doing a hypothesis testing, and if I conclude that Miller is a highly likely factor, I will take Miller to further investigation. If I conclude that Miller is not affecting to particle size, then my conclusion will be it is a lowly likely factor, and then I will discard that factor for further investigation, for further analysis. What is worse, to conclude that this factor is highly likely when in reality is not affecting to particle size, or to conclude that this factor is not affecting to particle size when in reality it is affecting, it is creating an effect on the particle size? Well, for this specific situation, it is worse to conclude that Miller is not affecting to particle size when in reality it is affecting to particle size. And the reason of that is because if I conclude that Miller is not affecting to particle size, I won't investigate in more detail further that factor ahead, because I will discard that as one of the potential factors that is creating variability. So this is a big issue. But here, what will it happen if I conclude that particle size depends on the Miller, so Miller is a factor, it is a highly likely factor, when in reality, Miller is not affecting to particle size? Well, what I will do is that I will take that factor as a highly likely factor, and I will take it to further investigation. But the worst thing here is that later in the process, during the investigation, my conclusion will be, oh, guess what? This was not a significant factor, and then it will represent a minor rework because I'm taking a not significant factor for further investigation, and later I will realize that that's not a significant factor. So this is not a big issue, but this is a big issue. Both risks, they are highly correlated each other. If I want this to be small, this has to be high. If I want this to be high, this has to be small. So they both are highly correlated. Because I want to keep this one small, then I will take alpha big, and then I will take a big risk. Of course, it depends of what you are talking about. Because, for instance, let's say that I have developed a vaccine for COVID, and my conclusion is, the difference is big, is significant between the population that is not having the vaccine and the population that is having the vaccine. This vaccine is useful. That is great, but in reality is not. Then I will be using a vaccine that is useless. And of course I want this to be small, and if I want this to be small, this has to be big. But in this case, perhaps alpha shouldn't be 1%, but should be even smaller, maybe 0.01, that means 0.1% or something, even very, very small. Because the implication of concluding that this vaccine is useful when it's not are high, are really bad. So again, I wouldn't jump immediately alpha equal to 0.05 or alpha equal to 5%, and that's a general rule. Don't do that. It depends of what is in risk. It depends what you are talking about. So again, for this specific example, which is the problem solving to identify which are highly likely and lowly likely, I prefer to take lowly likely to further investigation than discarding highly likely from the investigation. Then that's why I will use an alpha, again, for this specific example, of 10% or alpha of 0.1, which is a big risk. Next step, validate the representativeness of data and check normality for each sample. I'm not going to talk about that one now. I remind you that there is another video in YouTube, here in the problem solving channel, about representativeness of data. And I'm talking about checking outliers, checking independence over time, which is Durbin-Watson, checking normality test, for instance, so etc. I recommend you sample size, for instance. That's another of the one of the tests. So you have to validate that. At this point, I will assume that the data that I'm having is not having any outliers. I'm assuming that both are normally distributed, and I will assume that they are independent over time. Then I'm having a representative sample for Miller A and the representative sample for Miller B. So next step is select test to use. As I have said, and you will see in the diagram that is being displayed, if I want to test two means, independent samples, normal distribution. And for that reason, I will be using the t-student test for two samples. Then select test to use, t-student test. That is the statistic that I will be using. Now, next step, calculate standardized test statistics. It depends of what test I'm using. Of course, since I have selected t-student test, then I will be using the standardized test statistic. The standardized test statistics for t-student is given by this formula. So the mean of the first sample minus the mean of the second sample minus the mean of the population 1 minus the mean of the population 2. Mean of population 1 is this one, mean of population 2 is this one. So mean A minus mean B, the difference is equal to 0, because I'm assuming that both are the same. Then if I subtract one from the other one, the difference will be 0. which is this one. And all of that divided by the standard deviation of the first sample square divided by sample size of the first sample plus the variance of the second sample square, the variance divided by the sample size of the second one. So I will be calculating this value. And well, let's do that. Let's calculate the the standardized test for T students. So, as I have said, T standardized, T calculated, is equal to mean 1, which in this case is 14.17, minus mean 2, which is 9.67, all of that minus mean 1 minus mean 2, and I have said since both the null hypothesis is that they are the same, then this difference has to be 0, must be 0, divided by standard deviation 1, which is 2.317 square, because that is the variance, divided by n1, the sample size is 6 for the first sample, plus the standard deviation of the second sample, 2.16 square, divided by 6, which is the sample size of the second sample, and all of that square root. Okay, let's do the calculations. The value for the standardized test statistics, in this case is T student test, is 3.48. Then that means that T calculated, the standardized test, let me call it calculated, is equal to 3.48. Next step, 8, sketch sampling distribution. What I have to do is to sketch the T student distribution and define the critical points in the distribution. So basically, the T student distribution is very similar to the normal distribution. It's a little bit fatter, but also it's kind of bell shape, symmetric, and the center is having a value equal to 0, for instance. And well, for this T student distribution, I have to identify at what value of T, because here are the values of T, at what value of T we have a point where the value, the area of the distribution, greater than that value will be 5%. I have to find at what value of T, of course negative T in this example, we are having an area below that distribution, then the risk is 5%. Why 5% and 5%? Well, the reason of that is because I have established an alpha of 10%. And I have established that the alternate hypothesis is that they are different. So I am splitting the 10% in two sides, greater than and smaller than. And that is the reason of why that 10% has been divided, and here we are having 5% here and 5% here. Once that I have defined those values, and these values can come from tables, T student tables, then I will be comparing the T calculated value against this distribution. If the T calculated that we are obtaining is in this region, is somewhere between this and this value, or this and this value, this is the area of fail to reject the null hypothesis. But if I'm having this value calculated is greater than this value, or the value calculated is smaller than this value, then I have to reject the null hypothesis, because this area I will reject null hypothesis, and if I reject the null hypothesis, then I will accept the alternate hypothesis. My conclusion will be that Miller is affecting to particle size, because particle size are different between Miller A and Miller B. Same thing here. If the value calculated is smaller than this critical value, then this area will be the area of reject null hypothesis. Reject null hypothesis. So, what's what I have to do? Well, find out what these values are. And, well, let's take a look to the tables to find those values. Taking a look to table T student, we have to select the column related to the alpha risk that we are taking. For this case, in one tail, we should take 0.05, and for two tails, 0.1. That means 10% for both tails or 5% for each tail. Now, what rows should we take? The row, it depends on the degrees of freedom. The degrees of freedom are given by the first column. But question, what should be the degrees of freedom? Let's go back to review how to calculate degrees of freedom. We can calculate the degrees of freedom using this formula. So let's do that. The degrees of freedom is equal to the standard deviation of the first sample, 2.317 square, divided by n of the first sample, which is 6, plus the standard deviation of the second sample, 2.16 square, divided by n2, n of the second sample, also 6. All of that square. And then let's divide that by standard deviation of the first sample square divided by n6, all of that square, and all of that divided by n of the first sample, 6 plus 1, which is 6 plus 1, plus standard deviation of the second sample, 2.16 squared, divided by n of the second sample, which is also 6, divided by n of the second samples, the sample size plus 1, which is 6 plus 1, and by the way, this part is also a square. And all of that minus 2, minus 2. Okay, let's do the calculations. Well, the degrees of freedom are about 12. Then we are ready to get from tables the value of t, alpha divided by 2, degrees of freedom, which in this case is t. For each tail will be 0.1 divided by 2 and 12 degrees of freedom, which is equal to, let's take a look to the table. Taking a look to T student table, with alpha for one tail 0.05 or for both tails 0.1 and degrees of freedom of 12, T is equal to 1.782. Then value T calculated will be here, which is 1.782, which is the value from table. Then T calculated is 1.782. And also negative, which is minus 1.782. So the next step is to compare the standardized test statistics, which I call T calculated 3.48, and we have to compare that value against these critical points. And 3.48 is somewhere after 1.7082. Let's say that is somewhere here. Here we are having the t calculated, which is t calculated equal to 3.48. Well, what is the meaning of that? That means that this value is in the region of reject. So we are rejecting the null hypothesis. What is the null hypothesis? The null hypothesis is that the mean of particle size for Miller A is equal to the mean of particle size for Miller B. We are rejecting that, and then if we reject the null hypothesis, we have to accept the alternate hypothesis, which is that the average or the mean of particle size for Miller A is different than the mean of particle size for Miller B. In other words, since the particle size are different, that means that the practical hypothesis is correct. The particle size is different between Miller A and Miller B. So we can conclude that this difference is significant, different from a significant, from a statistical point of view, because we are rejecting the null hypothesis. Which means that if we are rejecting the null hypothesis, that means that the factor Miller is a highly likely factor, and we have to take that factor for further investigation in our problem-solving process. Okay, well, that's it in terms of two samples, independent normal distribution. Before moving to other type of hypothesis testing, I would like to talk about what about if the alternate hypothesis, instead of being different, is greater than or smaller than. Let's talk about that. Well, previously we have established that the null hypothesis is that the mean of particle size for Miller A is equal to the mean of particle size for Miller B. And I have established that the mean for particle size of Miller A is different than mean of particle size for Miller B. But what about if I want to align the alternate hypothesis to the practical hypothesis, and the practical hypothesis states that the mean of particle size for Miller A is greater than the mean for particle size of B. That means that the alternate hypothesis, instead of having different, I have to establish this greater than. What changes in terms of the procedure to do the hypothesis test? Nothing changes but just one thing. So we have to do the same thing. We have to establish our alpha risk. We have to validate the representativeness of data. We have to select the test to use. In this case, the mean is the same. T-student test, because I'm having two independent samples, normal distribution, small size. We also have calculated the T-calculated, which is the standardized test statistic. But what changes is here. Now, instead of divide the alpha, the risk, in two tails, I have to establish the value of alpha, all the risk in one tail. So now, the T-student distribution will be something like this. We are having our T-student distribution. We know that the center is in value of T equal to 0. But now I have to find out a point. The critical point will be the one where the T calculated, no, the T of tables, let me say tables, is a point where this area will be 10%, which is equal to alpha. Now, I'm not going to divide alpha in two tails. I'm not going to divide 5% to the right, 5% to the left. But because the alternate hypothesis is greater than, then the whole risk will be only in one tail. Then let's, what I have to do is to identify on tables what is the value where the area below the t-distribution is 10%. Then that means that what will change will be here. What I have to change is this. Instead of alpha divided by 2, will be just alpha. And then I have to take a look to the table and selecting all the risk in 10% only in one tail. So let's do that. For t-student distribution, and taking that in one tail an alpha of 0.1 and 12 degrees of freedom, t-value, instead of being 1.78, it is 1.356. Then the value of t of tables is 1.356. And that is the critical point, 1.356. Now I have to identify where the standardized test statistics will be in terms of the distribution. So the t calculated is 3.48. 3.48, which is, let's say, t calculated, not t of tables, is having that value, is having 3.48. So the conclusion will be the same. This value is in reject area. Keep in mind that this is fail to reject null hypothesis. And then here we are having in region of reject null hypothesis. Because this value is in this region, then we are rejecting the null hypothesis. We are rejecting that the particle size is the same for both Millers. And then we are accepting that particle size is bigger for Miller A than for Miller B. Well, there is something else that I would like to add here. And this is very important. In both cases, well, which is basically the same, but I have just changed the alternate hypothesis, I have rejected the null hypothesis, which means that the factor is highly likely. There is a significant difference from a statistical point of view. But what about if we were having a value in this region, on this region? If the value calculated, the standardized test value calculated, were in this region, does that mean that the means are the same, assuming that we are in that area, that we are not rejecting the null hypothesis? Should we accept that they are the same? And the answer is no. We never ever are going to accept that they are the same. We have two options. Option number one, reject null hypothesis, and if we reject null hypothesis, we will accept the alternate hypothesis. Good. Certainly, they are different. That factor is significant, and then that's a highly likely factor. We can take that one. But if we fail to reject the null hypothesis, that doesn't mean that they are the same. What we should state is there is not enough statistical evidence to conclude that the means are different. Then we will assume that they are the same. But that is an assumption, that is not a fact. So we may assume that they are the same, but that doesn't mean that they are the same. So in reality, as I have said, we will never accept the null hypothesis. We will reject, and if we reject, we accept the alternate, or we will fail to reject the null hypothesis. Which means that if we fail to reject the null hypothesis, there can be two possibilities. Possibility number one, maybe they are different, but the difference between those two is very small, and because of the noise of the natural variation, we don't have enough statistical evidence to conclude that they are different, because we cannot see the difference because of the noise that is created by the many other factors that are affecting to the response, that are affecting to the variable of interest. So maybe they are different again, but my sample size is not big enough to be able to conclude that they are the same. So maybe they are different, sample size is not big enough, or the noise is too big and I cannot see the difference. But maybe they are different. Or maybe they are not different. Maybe they both are coming from the same population, and that factor is not significant at all. But as I have said, I won't know that. I won't be able to make any of those conclusions. I cannot say they are the same, or I cannot say maybe I need a bigger sample size. So at the end, what I should say is I don't have enough statistical evidence to conclude that they are different, which means that the difference that exists, if exists, is not significant from a statistical point of view. That is very important. Okay, let's move to other type of hypothesis test. Okay, now I would like to talk about hypothesis testing when I want to compare two samples, two means, normal distribution, but the samples are dependent, not independent. The previous hypothesis testing was for independent samples. And that means that we are having two samples, but for instance, this value should be the same than this one, or this other one should be the same than this one, or this other one should be the same than this one. So they are dependent each other. One of the situations where that can happen is when you want to validate measurement systems, for instance. But instead of doing a gauge R&R, a repeatability and reproducibility study, for instance, you want to validate the measurement systems using hypothesis testing. So in the example that I'm having here, you are doing the same measurement for different parts, and for part 1, you are having the measurement of that part in instrument R23 and the measurement for the same part on instrument J87. So it is supposed that those two measurements should be exactly the same because both are measuring the same sample. In that case, then, I would say that though I am having two samples, but the measurements are dependent each other, or the value should be dependent each other. I should not use the previous hypothesis testing because, for instance, let's say that I'm having instrument 1 and instrument 2, and for those two instruments I'm having these measurements 1, 2, 3, 4, 5, well, let me do 6, and 6, 4, 6, 5, 4, 3, 2, 1. Certainly, if you do the average of these values and the average of these values and the standard deviation of those values for both of them, you are going to have exactly the same values for both. So your conclusion at the end for your null hypothesis will be that the measurement for instrument 1 is the same than measurement for instrument 2, and your alternate hypothesis can be that they are different each other. But your conclusion is going to be that you will fail to reject the null hypothesis because both means are exactly the same, both standard deviations are exactly the same, so certainly your conclusion will be they are the same. But that's not true, because this value is very different than this value is very different than this value, so at the end, although the means are the same, the specific values are totally different. Then that type of hypothesis testing is not the right hypothesis testing that we should run, that we should do for dependent samples. Instead of that, then we have to check differences. So let's do that. Let's do the hypothesis testing, but for differences. Then the practical hypothesis, it will be practical hypothesis. Both instruments perform same measurements. For instance, so I'm having one sample, and this sample will be done the same measurement for both equipments. Just to say, that's a wording thing. Maybe that's not the best way to state the practical hypothesis, but that's what you think. Now, the null hypothesis. For the null hypothesis, I have said that always is the same, but in this case is the same to what? I'm not going to compare both means, but the differences are the same, are equal to 0. And that's what I'm going to test. What I'm going to test is not the two means, but I have to evaluate the differences between those two. For instance, the difference here is 0. I can do the second one minus the first one. For instance, it can be 0.11. If I do reverse, then the next one will be negative. So those are the differences, and the hypothesis is that the differences are equal to 0. The alternate hypothesis, let me say that, well, the differences average, let me say that the differences average is equal to 0, and the alternate hypothesis, it can be that the average for the differences is, let me say, greater than 0 or different than 0. It depends what I want to test. Then I will establish the risk, and as I have said previously, it depends of each situation, but for this case I will state I will take a high risk, an alpha of 10% or a confidence level of 90%. I have to validate the representativeness of data, and I will assume that I'm not having outliers. I will assume that this is a normal distribution, and they are independent over time. So the next test is to select test to use. The test to use also will be the T-student test. So well, let's say that the test to use is T-student, but I will use that one for differences. Well, then the next step is to calculate the standardized test statistic, which for this case is the T calculated, but I will be using the average of the differences minus the mean of the differences. So let's do that. Let's do the calculations. Then what I need is the average of the differences, and that will be the average of these values. Okay, the average of the differences is equal to, let's do the calculations. Okay, we are having already the average of the differences. Now I want to get the sum of squares divided by the degrees of freedom, which is this term. The sum of squares will be the difference minus the difference average. Well, in this case will be 0.11 minus 0.11. In this case, this difference is 0. Minus 0.15 minus 0.11 minus 0.26. This minus this, minus 0.06. This minus this, minus 0.20. This minus this is 0.02. This minus this is minus 0.04, and this minus this minus 0.12. Now this term should be a square, which is the minus the average square. So I have to square each of the terms, and I have to get the sum of all of them. Okay, let me do that. We have just calculated the sum of squares. With that, we are ready to get the standardized test statistics. The standardized test statistics that we are using, it will be the T-student statistics for paired sample, which is given by this formula. Then, let's apply the formula. The T calculated is given by the average of the differences. In this case, the average of the differences was 0.11 minus the expected mean for differences, which is our null hypothesis. And our null hypothesis, the expected value for the mean of the differences, is equal to 0. Divided by the sum of squares, 0.1276, divided by the degrees of freedom. The degrees of freedom is given by the number of values that we are having. 1, 2, 3, 4, 5, 6, 7 values minus 1. And all of that is square root divided by the square root by the sample size, which is 7, as I have just said. Well, let's do the calculations. Then T calculated is 1.9956. The calculated standardized test statistics, which I will call T calculated, is equal to 1.9956, which is this value. The next step, step number 8, is to sketch sampling distribution. The sampling distribution, it will be the T-student distribution, which is used for means, small samples. In this case, we are talking about means for differences. Center will be 0. And now I need to find out the critical value for this T-student distribution. Since alpha is 0.1, then the critical value is a point where the area above that value, the area below the T-student distribution, after that value will be 10%. 10% of area, which is the alpha, the risk of 10%. And of course, this will be the critical value. The critical value is obtained from tables, T from tables. And then we are going to compare the T calculated. If the T calculated is in this region, that will be the region of fail to reject, null hypothesis. If T calculated becomes inside this other region after the critical value, well, that region will be the region of reject null hypothesis. So the next step is to get T from tables, and of course we have to get T for alpha 0.1 and degrees of freedom 7 minus 1, which is 6. Let's take a look to tables to get the critical value. Taking a look to T-student distribution, for alpha in one tail equal to 0.1 and 6 degrees of freedom, the T value is 1.440. Then T from tables with alpha 10%, 6 degrees of freedom is 1.44, and that becomes the critical value, 1.44. As I have said, I now need to find out where we are having the T calculated value. T calculated value is 1.9956, and 1.99 is after 1.44. Let's say is somewhere here. Here we are having T calculated, which is equal to 1.9956. That means that T calculated is in this region, which is the reject region. This is reject null hypothesis. Since we are rejecting the null hypothesis, then we have to accept the alternate hypothesis, which means that the mean of the differences is not equal to 0, but it is greater than 0. Therefore, my conclusion in terms of the practical hypothesis is it will be that both instruments are not measuring exactly the same thing. Maybe there's a differences, well, in fact there is an average differences between those two of 0.11 units. That means that now we need to adjust one or both of the equipments, or well, we have to use some factors in order to adjust after the measurement be done. Well, basically that's it in terms of means dependent, which means that we are having paired t-test because the samples are small. Now, very quickly, I would like to talk about comparing one mean against one specific value. Let's say that here we are having values of my systolic pressure. So let's follow, let's follow the procedure. So let's say that the practical hypothesis is that my systolic pressure is normal. The null hypothesis is that the mean of the systolic pressure is equal to 120 because that is the normal value. The alternate hypothesis, let me say that the mean for the systolic pressure is different than 120. Alpha risk, let's say that this is the same, high alpha, 10%. I'm assuming that I have validated the data. I'm assuming that I'm not having outliers. I'm assuming that we are having a normal distribution, that they are independent over time. I don't have trends and so on. And now select the test to use. Since I'm using a normal distribution, a small sample, I will use again the t-student test because it's a small sample, a normal distribution, then I will use the t-student test. Now I have to calculate the standardized test statistic, and for that one, here I'm having the formula for the standardized test statistic. So in this case, is the mean, the average of the sample is 119.75, so is 119.75 minus the expected mean, which is my null hypothesis. The mean is 120, divided by the standard deviation, which is 5.1755, divided by the square root of n. N is the sample size, which is 8. Okay, let's do the calculations. Well, the calculated t will be 0.137 negative, and well, that's the value that I will write here. So the t calculated, which is the standardized test value for t, this calculated is equal to negative 0.137. Now I have to sketch the sampling distribution. As I have said, the t-student is a distribution, is similar to the normal distribution. The center is 0, and since I have decided to write here different, that means that half of the risk will be to the right tail and half of the risk will be to the left tail, because I have done different than, which in this case will means that here I have to define a limit, another critical value, and the area below the t, below the distribution, the t distribution, the area here will be 5%, and the area here also will be 5% to get the 10% of alpha risk that I'm getting. Now I have to define from tables the t for alpha divided by 2, n minus 1 degrees of freedom. In this case is 0.10 divided by 2, which is 0.05, and degrees of freedom 8 minus 1, 7 degrees of freedom. Well, let's take a look to the table. For t student distribution, alpha in one tail 0.05, in both tails 0.1, and degrees of freedom equal to 7, we are getting a t value from tables of 1.895. Then t from tables 1.895. That means that the value here, t of tables, and here minus t of tables, is 1.895 and minus 1.895. Then I have to find out where the standardized test statistic calculated, the standardized test student is. So for this case, the t of a student calculated was minus 0.137. Minus 0.137 is somewhere very close to 0, negative a little bit, and let me say that here the value is minus 0.137. That is the t calculated. This region is the region of fail to reject null hypothesis. And what would be the meaning of that? I would say that the null hypothesis is that my average, or well, the mean of my systolic pressure is 120. Since I failed to reject this one, I'm not rejecting this one, that means that there is not enough statistical evidence to conclude that the mean of my systolic pressure is different than 120. Then I will assume, that's an assumption, that's not a fact, I should not conclude that is the same, but I will conclude, I will assume that the mean of my systolic pressure is equal to 120, but that's an assumption. So that means that I'm not rejecting a null hypothesis, I should not accept the alternate hypothesis, then I fail to reject the null hypothesis. Well, basically that's it in terms of small samples, normal distribution type of statistical hypothesis testing. Well, now I would like to talk about small samples and large samples. I have already taught what hypothesis test to use when we are having normal distributions and small samples. But if we are having large samples, then we can use the Z distribution or the normal distribution, because the sample is that large that the parameters of the sample will be very similar to the parameters of the population. Therefore, we can use the normal distribution that is used for populations. But I would like to mention this one. Of course, we are using the same procedure. We are following the same procedure. The null hypothesis, it depends. For instance, it can be that the mean is equal to one value, or one mean is equal to another mean, to a different sample. I mean, both samples are having the same mean, or both populations are having the same mean. Risk, 10%, as I have recommended for these specific cases. We have to validate the data, the representativeness of data, and we have to select the test to use. For normal distributions and the large sample, the test to use can be the Z distribution. For small samples, the distribution to use is the T student test distribution. But calculate the standardized test statistics. Well, I have said that this will be the formula to use for the calculated t when you want to compare one mean against one value. And for independent samples, I have said that this is the statistic to calculate, the t-value to calculate when we are having independent samples, small samples. But if you are having large samples, instead of using t calculated, you will be using z calculated. And as you can see here, if you compare those two, they are exactly the same. The only thing that changes is that here we are having the standard deviation of the sample, and here we are having the standard deviation of the population. But we are assuming that this standard deviation is of the population because the sample is that large that the standard deviation of that big sample is the same than the standard deviation of the population. But actually, they are exactly the same. And if you compare those two, you will see exactly the same thing. The only thing that changes is the standard deviation, but again, that's a definition because this is large and this is small. So both will be exactly the same. Now, to sketch the sampling distribution, which is step number 8. Well, the sampling distribution for large sample will be the normal distribution, and the t-student distribution will be the one for the small sample. Both are symmetric, both are having 0 at the center, but the value of t will depend on the alpha, the risk, and the degrees of freedom. And by the other hand, for the normal distribution, the z-value won't depend on the degrees of freedom because the sample is that big, is that large, that we are assuming that the sample size is infinite, or that large, maybe thousands of values or big numbers. So there won't be a change in terms of the value. So basically, it depends on alpha. By the way, if your alpha is 10%, the z-value is 1.645, and if your alpha is 0.05, your z-value calculated is 1.96. But usually what I do is that in most of the cases, my personal experience is that I prefer to use for all the cases, for everything, the t distribution. And the reason of that is because when the degrees of freedom are infinite or the degrees of freedom are very high, the value of t is the same than the value of z for when the sample size, when the degrees of freedom are very big. So at the end, if you want to use for the whole cases, small samples or large samples, the t-student distribution, you will be safe. There won't be major differences, and especially when we are doing problem-solving process like the ones that we are following. Well, basically that's it in terms of hypothesis testing when you want to compare means, hypothesis testing for means, by the way, normal distribution. Thank you very much.